Hi everyone, so today I'm going to talk to you about some of our work on simultaneous discovery of coordinates and parsimonious dynamics. So traditional methods for modeling physical systems involved deriving governing equations from first principles or universal laws such as conservation laws or gravity. As an example, I can show you this video of a pendulum here. Now, we can easily derive a simple equation for describing the behavior that is seen in this video, the behavior of the pendulum, with one equation in a single variable, that is the angular position of the pendulum. And we can just do this using Newtonian mechanics. A more interesting example is the Navier-Stokes equations. The Navier-Stokes equations were also derived using first principles, conservation of mass, energy, and momentum, and they're written down here. The Navier-Stokes equations are widely used for modeling fluid flows, and they're used in applications such as climate modeling and engineering of design of cars and airplanes. However, there are many systems for which we do not have a known set of governing equations. For example, this video here shows activity in a mouse brain. We don't have a clear known set of governing equations that describes the overall activity seen in the brain, and deriving such an equation from first principles has proven very challenging. So this motivates methods for discovering such governing equations from data, and particularly from high-dimensional data sets that are now becoming more readily available, such as this one. So today I'm going to focus on the goal of turning high-dimensional scientific data into parsimonious dynamical models. So as an example, again, we can consider the pendulum. So here I have high-dimensional data in the form of this video of the pendulum behaving, and the goal would be to discover a low-dimensional parsimonious dynamical model, that is the pendulum equation, from this video. So in order to do this, we need to be able to identify both the coordinates in which the dynamics become simple, and then we also need to be able to identify the dynamics. So we need to be able to pull out that the angular position of the pendulum is the right variable in which to represent the dynamics simply. So the method I'm going to talk about today performs a simultaneous discovery using an autoencoder to identify the coordinates and SINDy to model the dynamics. So to start telling you about our method, I'm going to start with an overview of SINDy. So SINDy is a method introduced in 2016. This is the sparse identification of nonlinear dynamics. So for SINDy, we assume that we have measurements of some data X, and we have snapshot measurements of this data in time. So these are your state variables of whatever system you're interested in. And we just assume this is a vector in Rn, and you have snapshots collected over time. We assume that this data X was generated from some underlying dynamical system in the form seen here. So we have some function f, which describes the dynamics. The idea of SINDy is that we don't necessarily know f, and we want to discover it from measurements of x. So as an example, we can just consider the canonical Lorentz system seen here. So here we have a set of three equations. So this is a state variable in 3 dimensions. And this set of functions on the right-hand side here make up our f that describe the dynamics. And then we can see the dynamics in this plot here. So the goal here would be to take measurements on this attractor and discover the form of f that generated this data. So SINDy is based on the observation that for many physical systems of interest, this function f is actually sparse in the basis of possible functions. So for many physical equations that we're interested in, we only have relatively few terms in this function f. For example, when we're looking at this Lorentz system here, even if we only consider a basis of polynomials of your state variables up to cubics, there are still relatively few terms in the dynamics in this equation. So SINDy sets up the problem of discovering the underlying equations as a sparse regression among a library of possible terms in your function f. So now I'm just going to show you a real quick walkthrough of how SINDy works. So we assume we have some set of measurements that come from some underlying unknown true system, such as our Lorentz system here. So we take derivatives, we either measure the derivatives or assume we can calculate them from our snapshot measurements of x, and then we stack these time derivatives into a matrix. So here in this matrix, each column is a time derivative of a different state variable, and each row is a measurement or calculation of the derivative at a different time. We then create a library of possible candidate functions that are going to be in our underlying dynamical system. So here I've just enumerated functions in the state variables. These are polynomials up to cubics. And again, each row in this matrix is going to be a measurement at a certain time point, and each column here is going to be a candidate function in the underlying dynamics. So SINDy then performs a sparse regression to identify the terms in the dynamical system of interest. So here I've highlighted the terms in this Lorentz dynamical system. So you can see that even in this very limited basis, the true underlying system is indeed sparse. So from this, we now get an identified system, and we hope that the system we identified has a close match for our true dynamics. So SINDy works well if we know the right set of state variables to measure. So in this Lorentz system that I showed you here, I told you what the state variables are, and we can easily write down a set of equations that govern the dynamics in this set of variables. However, for many real-world systems, we don't actually know what variables to measure. We don't know what variables are responsible for describing the true underlying dynamics that are seen. And this is particularly true for high-dimensional data sets. So many data sets these days are specifically high-dimensional. And for example, a lot of them will have measurements at different spatial locations, or we might have high-dimensional video data. So here I'm showing a video, again, the video of the pendulum, as well as a spatial representation of a PDE. So this is a simulation of a reaction diffusion system. And in systems like this, if we just are given this high-dimensional data, we don't necessarily know which coordinates are right to represent the dynamics that are going on in this high-dimensional data. So this motivates in combining some sort of method for discovering coordinates with SINDy. So one particular thing you might think about doing is just applying a standard dimensionality reduction method to these high-dimensional data sets in order to get a simple set of variables, and then you could try to form a SINDy model on that representation that comes out. However, this can potentially have limitations. So if you just apply a standard out-of-the-box dimensionality reduction method, you don't necessarily know that the coordinates are the right coordinates to find a simple dynamical system. So this is why we want to perform a joint discovery of the coordinates and the dynamics. So today I'm going to talk about a method we've developed for doing that. In particular, the method we introduce uses autoencoders for discovering reduced coordinates. So I'm going to start talking to you about autoencoders. So an autoencoder is essentially just a simple feed-forward neural network, but rather than training it to do some tasks such as classification or prediction, you train it to reproduce its input as its output, and then the goal is to identify some set of intrinsic coordinates or latent code that hopefully tells you something interesting about your data. So you can see the loss function for the autoencoder down here. If I'm giving it some high-dimensional input data X, I simply want the autoencoder to be able to reproduce that data. And then I'm going to map through this hidden layer that represents the intrinsic coordinates and gives me some alternative representation of my data. So one common use for autoencoders is for performing a dimensionality reduction, and that is the specific task I'm going to talk about today. So in order to get an autoencoder to perform a dimensionality reduction, we simply specify that the hidden layer in the middle of the network has many fewer units than the original input data. And so in this way, you're training the autoencoder to essentially find some low-dimensional representation of your data that it can then use to recreate the data in its original form. So we're interested in finding reduced coordinates along with dynamics. So the idea for using an autoencoder here is to essentially combine the autoencoder with a SINDy model on the reduced coordinates. So in this way, you're essentially learning with the autoencoder a reduced representation of your data, and then you're learning an associated SINDy model in that reduced space. So you can combine these. We have the loss function for the autoencoder shown over there, and then the loss function for the SINDy model here. And we see that the loss function for the SINDy model in this case is just written in the z coordinates, the intrinsic coordinates of the autoencoder. So now we have the question of how do we do this training? So one way you could think to try to find such a model is to perform some sort of sequential training. So you could try to train an autoencoder to find a reduced representation of your data and then fit a SINDy model on the intrinsic coordinates that come out of this autoencoder. Unfortunately, this has the same issue I mentioned with using standard dimensionality reduction approaches, is that the autoencoder, when it's finding this reduced representation, does not know that you're interested in a dynamical model. And so the latent coordinates that it finds might not be well suited to finding a sparse, simple dynamical model. So instead, what we do is we perform a simultaneous training to learn both the reduced coordinates and the SINDy model at the same time. So essentially what we're interested in doing is, in addition to training the weights in the autoencoder network, we want to learn this set of coefficients that describe the dynamical model. So what we can do to do this is essentially we can rewrite the terms in the SINDy loss function using the autoencoder weights and then this coefficient matrix that you'll also learn, and then we can perform one training of the network and the SINDy model. So here you see we can rewrite the derivatives in terms of the gradients of the encoder, and then we can similarly rewrite the library functions in terms of the weights of the network. And then this just gives us a combined loss function shown here, which is rewritten in terms of the encoder weights and coefficient matrix. And then we can use this together to train the network. And I'll also add in an L1 penalty here just to encourage that we're finding a sparse dynamical model and not just any dynamical model on the data. So this is the essentially the setup that we use to train our network. So here we have one term in the loss function that is used to train the autoencoder and ensure that it's able to reconstruct our original data using this reduced representation. And then we have a SINDy component here that ensures that we have a good dynamical model, a good dynamical representation in the latent space. Okay, so now I'm just going to talk about how we actually train our network and go over a few examples. So today I'm going to talk about 3 example systems that we've considered. The first is sort of a proof of concept example where we use this original Lorenz system I introduced earlier, and we map it up to a high dimensional data set just to see if the network can recover this model from the high dimensional data set that we start with. The next shows a discovery of a reduced order model for a PDE. So we'll use a simple reaction diffusion system. And then the third case is trying to discover a physics model from video. So here again, I will use the example of the pendulum. So I want to highlight that when we're performing this training and analyzing the results, the thing that we are most interested in is the sparsity pattern of the resulting model. So when I talk about the examples we look at today, the main thing I'm going to focus on is, does the network recover this sparsity pattern or this right coefficient matrix for the SINDy model? Are we able to find the right form of the dynamics? So with that in mind, we're going to look at the sparsity pattern of the resulting models for all of these example cases. So one thing I wanted to mention is that I mentioned using an L1 penalty on the coefficient matrix in order to actually find sparse models. However, we found that in our initial experimentation, if we used simply an L1 penalty alone, this resulted in models that had many coefficients that were close to zero, but weren't truly sparse. There weren't actually only a few non-zero terms. And for finding the right sparsity pattern, we're really interested in a mask that tells us, like, these are the relevant terms in the dynamics. So in order to achieve this, we use an additional method in our training. So we did an additional step called sequential thresholding. So here I have our loss function shown here. So we use this loss function to train and encourage getting a SINDy model with many coefficients that are close to zero. But in addition, we perform sequential thresholding, which means that essentially at fixed periods throughout the training, we specify some threshold, and then at fixed periods throughout the training, we just set everything below that threshold to zero. So this gives us a way of kind of sequentially masking out the non-relevant terms in the dynamics. And in the end, this results in a truly sparse dynamical model. Okay, so now I will go over the examples that I've mentioned. So as I mentioned, the first example we look at is sort of a proof of concept example based on the Lorentz system. So here we want to know, if we have some low dimensional dynamics and we map this up to some high dimensional spatial modes, can we recover the original low dimensional dynamics? So this Lorentz system on the left here that I mentioned earlier is a dynamical system in 3 variables. So we're interested in, if we take modes that are meant to be spatial modes that are at a high dimensional on a high-dimensional grid, can we recover this simple 3-dimensional system from the high-dimensional data? So we take a set of fixed spatial modes, and then we just generate new high-dimensional data. In this case, we do it in 128 dimensions. And then we try to recover the original Lorentz dynamics from this high-dimensional data. So here I'm just showing you a representation of the true Lorentz model. So these are the 3 representations we're going to look at. We have the set of true equations up here. This is the SINDy coefficient matrix. And then this is just a picture of the attractor. So when we use our combined SINDy autoencoder, this is the model that the training procedure finds. So these are the equations again up top. This is the sparsity pattern from SINDy, and then this is the attractor. So a few things I'll point out here. One is, obviously these equations and this coefficient matrix are not the same as the original model. However, we do see that the coefficient matrix still has the same number of terms in the dynamics, and it looks somewhat similar to the original coefficient matrix. Also, the attractor clearly does not look like the original attractor. However, you can still see that there's a 2-lobe structure to the attractor. So what we found out by playing with this discovered system a little bit is that actually you can find an affine transformation on this discovered model that gets you to the original Lorentz model. So here I'm just showing a system that is an affine transformation of this discovered model. And you can see in this case that the equations are a very similar match, with the one exception being the coefficient on these Z1, Z3, and Z1, Z2 terms, which has a different magnitude than in the original system, but this is just kind of an arbitrary scaling. Now the coefficient pattern matches, and the attractor looks very similar to the attractor for the original system. So it appears that this method was able to discover a model that is essentially the true Lorenz model. So the next example I'm going to talk about is based on a simple reaction diffusion system. So we wanted to show an example to see if given high-dimensional spatial data from a PDE, we could discover a reduced order model for the PDE. So in this case, we're working with a reaction diffusion system that just has a simple spiral wave shown here. And this the activity in this video can be well captured by just a set of two oscillating modes. So we wanted to see essentially, could the autoencoder discover a simple oscillating model for this, this data, or what would it discover? So we trained the network to discover a reduced model with two intrinsic coordinates. And this is one of the models that popped out of our SINDy autoencoder. So you can see here from the equations that it discovered a model that was essentially just a simple linear oscillation. This is a representation of the SINDy coefficient matrix. So you can see, obviously, with two terms, this is a sparse model, and then this is just the attractor in the reduced space. It also, in some cases, discovered this a nonlinear oscillation. So in this case, we included a sine term in the library of possible functions. And in some cases, the network found that using this sine term in the oscillation also provided a good representation of the dynamics. So this is a very similar system. And here again, we show the attractor in the reduced space right here. All right, so the final example that we wanted to consider was the idea of, could we discover a physics model from video data? So in this case, we're working again with the pendulum. Here, I'm using a simulated data set of the pendulum as opposed to the actual raw video that I showed you earlier. So here we essentially want to discover the pendulum equation from this simulated video. So we trained our network using this data. And in this case, we actually had to go to a second order SINDy model simply because the pendulum equation is a second order equation. But in many cases, the network was able to actually discover that the pendulum equation was the best representation for this data set. So here I'm just showing the equation as discovered by the network. This is a representation of the coefficient matrix, and then the attractor for the pendulum. In a handful of cases, the network actually discovered instead this sort of simplified representation of the pendulum. So this just discovered a linear equation instead of using the sine term that is present in the pendulum equation. Now this has slightly different dynamics, as you can see in the attractor here. And you actually, if you looked at the performance of the SINDy model, in this case, you'd see that the discovered linear model does not have as good of a prediction of the dynamics as this first model. And so if you're performing some sort of model selection, you'd be able to identify that the pendulum equation was the best model for the dynamics. But we just thought it was interesting that in some cases it ended up discovering this reduced or this simplified form of the pendulum equation. All right, so in summary today, I just told you about our SINDy autoencoder methods for discovering reduced coordinates and associated parsimonious dynamics from high-dimensional data. So our approach combined using an autoencoder for discovering reduced coordinates with SINDy for discovering parsimonious dynamics. And if you'd like more details, feel free to check out the full paper. Thank you.